Guys, welcome back to TechDose, and in this video we will look at find closest node to given two nodes problem, which is from Leetcode number 2359. Let's now read the problem statement. In this problem you are given a directed graph of n nodes numbered from 0 to n minus 1, where each node has at most one outgoing edge. The graph is represented with the given 0 indexed array edges of size n, indicating that there is a directed edge from node I to edges at I. If there is no outgoing edge from I, then edges at I will be equals to -1. You are also given two integers, node 1 and node 2. Return the index of the node that can be reached from both node 1 and node 2, such that the maximum between the distance from node 1 to that node and from node 2 to that node is minimized. If there are multiple answers, we need to return the node with the smallest index, and if it is not possible, then we need to return -1. Note that the edges may contain cycles. So in this case, the first point to note down is each of the node has out degree of maximum 1, so it can be 0 or 1. So if your directed graph has maximum out degree of 1, then you can represent the entire adjacency list by using a single dimensional array, right? So in this case, they have also mentioned that that single dimensional array is already given in the form of edges. So you don't need to make the adjacency list. It is already given in the problem. So if you look here, this is your adjacency list. Here you will find indices 0, 1, 2, 3. And this graph is represented like there will be a directed edge from 0 to 2. You see, there will be a directed edge from 0 to 2. From 1 to 2. Okay, you have from 1 to 2. Then it is saying 2 to 3. 2 to 3 and 3 to -1 means there is no outgoing edge from 3. This is how the representation is given. So we already have the adjacency list. We don't need to make it. And in this case, you will be given two nodes, node 1 and node 2. So in case of this example, this is node 1 and this is node 2. Now, if you find out the distance values from all the node 1 to all the nodes and from node 2 to all the nodes as well, then you will find that this is distance 0, distance 1, distance 2. Now node 1 cannot cover this 1 because it is not traversable. And for node 2, this node is at distance 0, this is at distance 1 and this is at distance 2. From node 1, node 0 is not traversable, okay? Now, if you find out the common nodes where they both can traverse, which of them is having the minimum distance? So node 2 has the minimum distance, right? Because it is taking one distance for 1 to reach here and one distance for 0 to reach here, right? So the maximum of the two distances will be taken and we need to minimize that maximum. So in this case, the maximum of 1, 1 is 1. In this case, the maximum of 2, 2 is 2. So out of these two available options, 2 and 3, this node 2 is a better option because this is the closest to both the nodes. Okay, and that is why node 2 is an answer. Now I hope the problem is clear. I will show you more examples. Now before looking at more examples, in this case the constraint says about 10 to the power 5 number of nodes. So definitely an n square algorithm is out of question because that will make it 10 to the power of 10, which will be way beyond your 10 to the power of 8, which is a standard for 1 second. So in this case, an order of n or n log n will work, but anything beyond that is not going to pass. Okay. Now let's look at more examples. In this case, I have made another example. This is example number 1. Here you can see that node 1 is 0 and node 2 is 7. So if you find out the distance values, I have marked it the node 1 distance values in green. So if you start from 0, 0 to 0 distance is going to be 0, to 1 it is 1, to 2 it is 2, to 3 it will be 3, 4, 5. And similarly, the distance values from 7 is 0, 1, 2, 3, 4. So what are the common nodes which are traversable by both node 1 and node 2? These are the common nodes, okay, 3, 4 and 5. So out of these, which is the node which is closest to both of the nodes? So it is 3, right? So therefore the answer in this case is going to be 3. If you look at the distance values, this 3 is at distance 3 from node 1 and at distance 2 from node 2. So we will be taking the maximum according to the problem statement. Take the maximum, it is 3, maximum of both the distances. In this case, this is also an option because it is traversable by both the nodes. So take the maximum of 4, 3, it will be 4. Maximum of 5, 4, it will be 5. And minimize the maximum. So that is going to be this 3 will be the minimum distance, but we need to return the node value, not the distance value. Okay, so 3 is the node. Fine. Now if you look at example number 2, in this case node 1 and node 2 are 0 and 2, and if you mark all the distance values from node 1, then this is going to be 0, 1, 2, 3, and for node 2 it is going to be 0 and 1 only for 2 and 3, because from node 2 you cannot traverse to node 0 or 1. So what are the common nodes which are traversable by both? It is going to be 2 and 3. And out of these two options, which one is the closest one? Definitely it is going to be 2, right? Because if you look at the distance values 0 and 2, try to take the maximum, it will be 2. 1 comma 3, try to take the maximum, it is 3. So you need to minimize the maximum, so this 2 is going to be the minimum distance. Okay, so in 2 hops they can come to the same point. When you do not move anywhere from node 2, but the other person moves from node 1 2 hops to the right hand side, okay, then they will meet. So node 2 is going to be the answer. If you look at example number 3, in this case node 1 is taken as 0 and node 2 is taken as 3. So what we have to do, step number 1 is to find out the distance values for all the nodes. So if you look at this node 1 value, then the distance is going to be you can say 0, 1 and 2. But for 3 it is going to be -1, and for 4 also it is going to be -1. -1 means it is not reachable. Okay. Now similarly for this node 2, which is 3, you can mark the distance values as 0 and 1 for 3 and 4, but you can mark all the rest of the nodes with -1 values, because 0, 1, 2 are not reachable from 3, right? So what we have to do now, you find out the values, like is there any common point where you have non-negative distance values? So there is no node where you have non-negative distance values, right? And therefore there is no common node which can be traversed by both node 1 and node 2, from both node 1 and node 2, and therefore there is no answer. So we need to return -1. So step number 1 is to calculate the distance values for traversal from both the node 1 and node 2. This should be our step number 1. And when you are done with step 1, then the step 2 should be to parse all the nodes like one by one, and we need to try to minimize the maximum of both the distances from node 1 and node 2, right? This should be the overall idea. I hope you have understood the idea. Let's now see how to solve this entire problem by using multi-source BFS. This is popularly used in the rotten oranges problem. If you haven't solved it, you can watch my video on rotten oranges. Now in this case, even if you haven't watched it, you will still be learning it from scratch. So I have already made a graph. Here you are given the edges. So this is the entire adjacency list, and we already know that we will be solving it in 2 steps. The first step is to find the distance for all the nodes from both node 1 and node 2. Okay. Now you know that at every node we need to maintain 2 distance values. Like if I write at 4, then the first distance value will say from node 1 what is the number of hops, and another distance value will tell you about from node 2, that means from 3, how many hops it will take to reach to this 4. So we need to save 2 different distance values for all the nodes. If it is not reachable from one or both nodes, it will be -1 for its corresponding values. So if you have n number of nodes, which is equals to the edges dot size, right? N number of nodes, then you need to take n by 2 size of an array, n by 2 size array. So simply you can take a pair of array, or you can take a matrix of size n by 2. So in this case I will be going with the matrix, which is called the distance matrix, which will help us in tracking all the distance values from node 1 and node 2 for each particular node. Okay. Now in this case, if you look at this matrix, then this 0 will say what is the distance of a particular node from node 1. Okay. And this one and this first column will say what is the distance value for a particular node from node 2. So if I say that at 3, 0 we have x, then this means that in order to reach to this node 3, there will be x number of hops taken if you start with node 1. If you check out the graph, actually it is not reachable, right? You cannot reach to 3 from 6, and that is why this x value will be -1. if it is not reachable. If I write for this 2 and write here x, then this means x hops will be taken from node 1, that means 6, and if you check, it will be 2 hops to reach to 2, right? So the final value which will be put here is 2. Similarly, if you think about what will be the value here, if it is y, then if you start from this node 2, then y hops will be taken to reach to this node 2. So 1, 2 and 3. So 3 hops is the minimum distance, and that is why this y value will have a final value of 3. So I hope you have understood this entire matrix. Now in this matrix, I will be pre-filling all the values with -1, indicating that none of the nodes are reachable, because you don't know what nodes are reachable right in the beginning. So I'll be filling all of them with -1. And you know that I will be starting the BFS of node 1 from the given node. In the example, it is 6. And that is why if I know I'm starting at 6, therefore the node 1 traversal from this 6 is going to be 0 distance. Wherever you start, it will be 0. And for node 2, that means the second traversal from 3, it is also going to be 0 distance, right? Now in our entire code, I will be denoting this with the number 0 and number 1 and using a type variable for it. That means which BFS are you doing? Are you doing type 0 BFS? That means the BFS going from node 1, starting from node 1, or you are doing type 1 BFS. That means BFS starting at node 2. So this will help us in understanding when we are at a node, then from which node have I actually started, and so which cell I should update. Okay. Why we are doing multi-source BFS? We could have done it by calling 2 times BFS, but I think doing it together is more optimal than doing it one by one. So that is why we will be going to do it together. So how to do BFS? We have to take a queue. As a standard BFS technique, we have to take a queue. And in the queue, you have to pass which node are you starting with. So we are starting with node 6, and this is a type 0 BFS. That means the BFS starting from node 1, and we are also starting at 3, which is a type 1 BFS. That means BFS starting from node 2. Okay. Now why this is important? This is important because if we traverse a node for the second time, then still it should be traversable if we are reaching there from 2 different sources. Like if we reach at 1 from 3, then later I will be reaching to 1 via 6 because the distance is more. In the multi-source BFS, we will be expanding from all the sources at the same time. Okay, so all the source will be expanding at the same speed, and therefore whoever is closer to 1 will be reaching to 1 first, and whoever is farther away will be reaching there later. Okay. So in the worst case, I will be traversing each node 2 times because each of the nodes are also having out degree maximum 1, isn't it? So let's do the BFS. You can do it the BFS in 2 ways. Either you do level order traversal by finding the size of the queue that I have done, or you can skip it. It is not required for this problem, but I will do it by finding the size. So in this case, find the size of the queue. At level 0, you have 6 and 3. Okay. So take out this 6. What is the traversal type? It is 0. So from 6, what is the adjacent node? It is 4. If the adjacent node was -1, then that means from 6 there is no outgoing edge, and that is why I will not process anything. You will just pop it off and go to the next node. But in this case, since there is an edge going to 4, I will be processing it. Now you check out at 4 for this type 0 BFS, what will be the distance value stored here? Whatever was the distance value to reach to the adjacent node 6, that is 0, to this I took one more hop to reach to 4, isn't it? So to 0 you add 1, and this will be 1. And then you have to push it back into the queue node 4 with a type 0 BFS, right? Similarly, you take out this 3, 1. Now from 3, there is an outgoing edge to 1. So look at this one. Okay, we are doing type 1 BFS. So at the previous node, that means at 3, the distance was 0. I took 1 hop. So here the distance is going to be 1. And you push 1 with the type 1 BFS. Now we are done with level 0. Again, find the size of the queue. These all nodes will fall in level 1. And now you again do the same thing. Take out 4, 0. So from 4, what is the outgoing edge? Outgoing edge is to 2. What is the type of BFS 0? So go to this 2 0 and look at the distance value at 4 0. It is 1. We took one more hop to reach to 2 from 4, and that is why the distance is going to be 2 here. Okay, and then we will be pushing this 2 with a type 0 BFS, right? Because we are doing type 0 BFS. Then you take out this 1 comma 1. Now from 1 we have an outgoing edge to 4. So go to this 4. This is type 1 BFS, right? Go to this 4 and column 1. So in order to reach to 1 from node 2, the number of hops was 1. So in order to reach to 4, number of hops will be 1 plus 1, that is 2. And then you insert 4 with a type 1 BFS, right? And we are done with level 1. Find out the size of the queue. These all nodes will fall in level 2. Then you take out this 2 comma 0. Okay, from 2 you have an outgoing edge to 1. So go to this 1 0, because this is type 0 BFS. You have reached to this 1 from 2. So in order to reach to 2, the number of hops was 2. So here it will be 3 hops. Okay, 3 hops. And then you will be pushing this node 1 with a type 0 BFS, and you are done. Now the next time you will be taking out 4 comma 1. From 4 you have an outgoing edge to 2. So if you go to 4 comma 1, okay, then the distance value is 2. Where we have to go? We have to go to 2. So at 2 comma 1, the distance value will be 2 plus 1, that because we are taking one more hop, so this is 3. So push this 2 with the type 1. Okay, and we are done with level 2. Now you find out the size of the queue for level 3. Take out this 1 comma 0. When you take out 1 comma 0, again you have to go from 1 to 4, isn't it? So take out 1 comma 0. Okay, go to this 4. So 4 comma 0. Now if you check out this distance value, if you go from 1 to 4 now, then your distance value will be 3 plus 1 4. Already known distance value is smaller, so we will not update it. Why did this happen? Because we cycled in this loop one time, isn't it? So if we are getting more distance value, then I will not take it. Okay, so we will simply drop this idea. We will not be taking it out. Now you go to 2 comma 1. So if you go to 2 comma 1, then from 2 you have an outgoing edge to 1. Okay, and this is type 1 BFS. So from 2 you have to go to 1, right? So you go to 1. From 2, if you try to go to 1 now, the distance value will be 3 plus 1, that is 4. But already known distance value is smaller. This is happening again because of the one time loop. Okay, the distance is increasing, and that is why I will not be updating it. I will drop this idea. And finally our queue will be empty. Once our queue is empty, I will be breaking it out. Now once you break out, all the unfilled values, since it was pre-filled with -1, will all be -1, right? And this will be the final distance matrix. So our step 1 is done, which was about finding the distance for all the nodes from both node 1 and node 2. So let me fill the values here. For node 0 it will be -1 -1, because node 0 is not reachable from either of the nodes, node 1 or node 2, right? Node 1 distance value is 3 comma 1, because if you see the number of hops it takes from 6, 1, 2 and 3 in order to reach to this 1, and this 1 is showing that it takes 1 hop from 3 to reach. For this 2, the distance value is 2 comma 3, so it takes 2 hops from 6 and 3 hops from the node 2, which is 3, right? Now for 3 it is -1 comma 0, because I cannot reach it from node 1, so it is -1. Now for 4 it is 1 comma 2. For 5 it is -1 comma -1, because nobody can reach to 5. And for 6 it is going to be 0 comma -1. Okay, for 6 it is going to be 0 comma -1, because from node 2 I cannot reach to 6. Now I haven't made the entry for 7. For 7 it will always be -1 -1, because 7 is in a separate component than node 1 and node 2. Okay, so we have taken 2 components, 7 is in a separate component, so it will always be -1 -1. Now once I have updated these values, now you can see them clearly. We need to minimize the maximum meeting point distance. How to do this? Now we have to just iterate through all the indices one by one. These are all the node values, isn't it? From 0 to 7. And we will be trying to minimize the distance, and wherever I get the minimum distance, I will be saving that node value. Now in order to minimize the distance, I will be taking the meeting distance to be infinity. Okay, because I want to minimize the distance and the meeting point to be equals to infinity as well, saying that I will not be able to meet. That means two nodes, node 1 and node 2, will not be able to meet at any particular node. And then we have to iterate and see if they can actually meet. So when you go to this node 0, where is this node 0? The first thing that you have to look at is both the distance values, not one, but both the distance values should be non-negative. Then only both the nodes can reach. But in this case, both are negative. Instead of both being non-negative, both are negative. So I cannot reach to this 0 node. So this will be skipped. If you go to node 1, then you see both the values are positive. Then that means both the nodes can reach here. So what will be the distance value according to the criteria? According to the problem statement, we have to minimize the maximum. That means the maximum of the two distances is actually taken out to be the distance to reach to this one. So the distance or the cost to reach to this one is going to be max of 3, 1, which is 3. Okay, so since this 3 is actually smaller than the already known distance value, so I will be updating it to 3. And since I have got a lower distance value, where did I get it? I got it at 1. So that is why I will be updating the meeting point to be 1. Okay, so this is the idea. Now I will be going to 2. When you go to 2, the max of this 2, 3 is 3. So is this 3 a better option than this 3? No, right? It is not a better option. Now this distance value is the same as this 3, right? So if it is same, then I will not be changing anything. In the problem statement, it was said that if two distance values are same, then we need to take the one with the minimum index. But since we are already moving left to right, that means we are already moving in increasing order of the index values. And that is why I don't need to update the index, because if I had already seen this distance value, then that must have been seen for a lower node value, isn't it? So that is why I don't need to do anything for it, right? Now I will be going to this 3. And if you look at this 3, where it is, you see one of the value is negative. So this is not a meeting point. If you see this 4, then both the values are positive. Take the max of these two values, which is 2. 2 is a better option than 3. Where did we update it? At 4. Okay, so 4 will be updated now. Now we will be going to the next node, which is 5. So at 5 we have negative value. So it will be skipped. It's not a meeting point. At 6. We have a negative value, so it will be skipped. At 7 we have a negative value, so this will be skipped as well. So after parsing through all the nodes, we found that the minimum distance is 2 and the optimal meeting point is 4. So we will be returning 4 as an answer in this particular case. So I hope it is clear. In this case, we are parsing this entire graph in step 1 exactly one time. So I will be considering this order of n complexity, because each of the node exactly have one outgoing edge. Okay, and we are traversing no more than 2 times for each of the nodes. In the second step, we are just parsing through all the nodes exactly one time. So that is also order of n. So the time complexity is going to be order of n, and the space complexity due to the queue will be order of n, because a node can have a lot of branches and all the nodes can be just present at the next level. So all the nodes may get pushed into the queue. So that is why space is order of n. And also we have taken the distance matrix, which is again order of n, right? So n plus n is going to be n. That is why the time complexity is O(n) and the space complexity is O(n). Let's now look at the code. If you are someone who is looking to prepare for top product based company within a limited time of just 3 months, then we have brought for you both the DSA and the system design live interview training program. The most important feature of this program is you get a filtered and condensed structured curriculum, in-depth discussion of all the topics, and my guarantee of your understanding, one-on-one guidance with me, and live weekend classes. To know more about the training, you can WhatsApp us on this given number. In this problem, we are given the edges, which is the adjacency list, node 1 and node 2. Now I will be finding the number of nodes, and as I already explained, the distance at A0, if it is x, then this means the distance from node 1 to node A is x. Similarly, if distance at A1 is y, then the distance from node 2 to node A is y. So in this case, I will be taking the distance 2D array and marking the node 1 type 0 with the distance 0, because this is the starting point and this is the second starting point, right? And now we will be performing the multi-source BFS as I had already explained. So I'll be pushing the first two nodes into the queue, which are the two start points, and then I will be taking out the front of the queue and checking if the outgoing edge is actually present. That means it is not -1, and also the distance value has to be equals to -1. That means it is not already traversed, not already reached. So this is also acting like a visited array for us, right? Not just storing the distance, but also marking the nodes which have been visited by a certain BFS will no more be visited again. And this is the updates, and I think the BFS is pretty clear. Now let's look at step number 2, which will tell us about minimizing the maximum distance of a node from node 1 and node 2. So here we will be taking the meeting point to be integer maximum and meeting distance to be integer maximum, which are infinity as I showed you. Parse through all the nodes one by one, and both the distance values have to be -1. That means both node 1 and node 2 should be able to come to that node, isn't it? So they both have to be -1. If that is true, then I can calculate the current distance, which is if the distance value is in the pair x comma y, then you need to take the max of x comma y, and that will be the current distance. And if the current distance is less than the meeting distance already known, then I will be updating the meeting distance and also saving the meeting point to be I. Okay, so this will already take care of if two nodes have same distance value, then the one with the minimum index will be saved, because we are going in the order from minimum index to maximum index, right? And after doing all the operations, if you could not find a meeting point, then it will be -1. That means there is no meeting point. Otherwise, we need to return the meeting point. So I hope the entire approach is clear, and if you still have any doubt, then feel free to comment below and I'll try to help you as soon as possible. See you guys in the next video. Thank you.